All right. Hello, everyone. So my name is Philippe Pasquier. I'm an associate professor at the School of Interactive Arts and Technology. And today, not surprisingly, I'm going to talk to you about the work we do in the Meta Creation Lab. We basically deal with generative systems at large. And so I want to acknowledge my colleague, Arnie Engelfield, with whom I co-direct the lab, and all the PhD, master, postdoc, research assistants, and undergraduate interns, students that are working with us on a day-to-day basis. So what is meta creation? I think we should start by that. And in order to introduce that, we'll start by introducing AI. So while the Industrial Revolution was about automatizing physical tasks, the information revolution, with all those information technology, is about automatizing the treatment of information, of symbolic information. And before computers, I exaggerate a little bit here, there was analog machines, but before digital information technology, the only thing that could process information was the human brain. And eventually some animals, over those there's some sort of debate around that. And artificial intelligence is really this idea of having machine solve problems that do require human intelligence typically to be solved, and automatizing this treatment of information. So that's just what artificial intelligence is. It so happens that it is striving, and as you know, we have a lot of computers around us on a day-to-day basis. We usually carry one on us, and there's a variety of problems and tasks that are achieved by machine very successfully nowadays. And so achieving those tasks is what we call in AI rational problem solving. And so examples are, we have AI systems that fly planes, that regulate nuclear plants, that design electric circuits, that automate negotiations between virtual agents, billions of dollars of transactions every day, and then diagnose disease better than doctors in certain cases, play chess better than me in most cases, and play Jeopardy. There's been a number of news last year about a system that was really good at doing that. So the list is quite endless, but what we are looking at in our laboratory is, can machine be creative? So those are all rational problem solving, and they're very rational oriented tasks. What about creative tasks? And so that's really the idea of meta creation, is to look at the practice and theory of automating creative processes. So sometimes this field is called computational creativity. Sometimes we talk about artificial creativity. But in general, the idea is always to try to endow machine with creative behaviors. So as a field, it's an academic field and an applied field. As a field, it's looking at both creativity as it is, in which case it's often part of cognitive science. How humans are creative, what are the models of creativity, can we understand creativity? If we can we simulate creative process in order to try to validate those models that are put forward by researchers. But it also looks at creativity as it could be. Once we move away from observing creativity as it is in the world, we can eventually think of creative process or expand, mix together those creative processes in algorithmic fashions to try to look at processes that we think would show the properties we observe as being creativity in human creative processes, but that we know humans are incapable of. Just because humans' memory is poor, humans' computing of information is quite slow, etc., etc. So there's possibilities here to go and look at processes that could not be possible with that machine. So we look at both. And we look at both the theoretical side, which is really computer science, and the applied side in terms of engineering and eventually applying those systems in a variety of contexts. So a question I get a lot when I go to conferences, AI conferences and machine learning conferences by my colleagues, is how is that not just AI? And the way I answer the question is by saying that in AI in general, the notion of optimality is very well defined. So in chess, there's a win or lose. When you fly a plane, there's a particular trajectory that is optimal to get from A to B, and that the plane is trying to follow, etc., etc. And in general, in AI, we talk about goal states, Pareto dominance, that's in game theory and in economy for negotiation, objective functions, utility functions, preference relations. That's how economists and people that do rational problem solving model humans and do rational problem solving. We are interested in the context of the lab and and meta-creation to look at creative tasks, which are precisely the task for which there is no such clear, crisp definition of what a best outcome is, what an optimal outcome is. So when you look at directing a movie, composing music, interpreting a piece of music, putting toward a joke, a choreography, there's no such thing as the best in any of these domains. There's no such thing as the best recipe of spaghetti, etc., etc. So all those tasks, which is quite large, it's not just the art, design is included, and a lot of other tasks do not have any clearly defined best optimal outcome, and the mathematical specification of those tasks is at least really, really hard to do. And therefore, for computers, it's hard to address. Why does it matter? Why would we want to have computers achieving those creative tasks, right? Well, there's many reasons for that, but I'm just going to stick to 4 of them here. The first one is fundamental research on creative processes. It's also fundamental research on the generative aspect of AI and on machine learning. If we could address those tasks, obviously those fields would just embrace and solve more problems. And in terms of the fundamental aspect when it comes to cognitive sciences, creativity is a complex phenomena. The brain is a complex, and intelligence in general are complex phenomenon. And for complex phenomenon, like for the weather forecast, the only thing we can do is, because the model is so complex, that we can't really tell, looking at the model, if the model is right or wrong. The only way to validate the model is to make simulations using computers. So we kind of have to, that's the current dominant methodology in cognitive science to validate theories, right? Either you make empirical experiments or you make simulations where you have your model making prediction and you validate those predictions against empirical evidence. Typically, for example, for the weather forecast, you get a lot of weather stations everywhere. They compute the current model of the weather, and because the computer iterates really fast in time and space, the computer will give you a prediction of what the weather should be in 3 days according to the model, and then 3 days later you find that the model was wrong. And then you come back to the modeling stage, right? Or maybe sometimes the model is right. So that's the first reason, fundamental research. The second reason is much more pragmatic, is that rational problem solving is not, it used to be for a long time, is not the main use of computers nowadays. The main use of computers nowadays, the main use of CPUs on Earth as we talk, is entertainment computing, especially gaming, and creative computing. It's people, making transformations on pictures, putting together their holiday movies, exporting, importing videos, all these more creative tasks for which there's no optimal solutions, optimal way to do it. People composing music with their computer, people doing design with their computers, etc., etc. And it so happened that for those software that are useful for doing that, there's very little automation. And so the real power of all we know about AI has not been transferred to those software at all. When you're a designer and you want to do a poster, and here grad students know that they have to do posters for conference now and then, you have a clear idea of what you want the poster to look like, and you're going to click on buttons one by one for hours, days, and for professional designers, sometimes weeks. You can't just tell the computer, look at those 5 posters I did last year, this is the new content, give me 3 mock-ups, and I'll start from there. You just can't do that at the moment, right? In fact, we have all the technology needed to enable that to happen. It's just that nobody's doing it. At least before we started working on that. And a third reason is the move from linear to nonlinear media that entail the explosion of the number of assets needed to create content. And at CIAT, the School of Interactive Arts and Technology, this is a key element. As soon as you have interactivity, you start to have interactivity when there's a relationship between the user and the content, such as it's not just the content is there and I get it fitted, is that I have a say in the development of the content. So the idea of the branching. So whether it's in a game, I can decide to go right or to go left. Each time there's this sort of branching, that's what enables interactivity in any given system, right? And so concretely, when you do a 1.5 hour linear media, such as a Pixar animation movie, you can have a team of 100 people working for 2 years on it. Every second can be looked at really, really carefully, and it's going to be fantastic, and it is fantastic. But when you develop, let's say, a video game, you have 12 million players, they play 20 hours per week, you need many, many new characters every week, many, many new worlds to explore every week, many, many new music pieces every week. In fact, how many do you need? The answer is way too many, which is why now for nonlinear media, the budget of production is a little bit out of control. It's a lot bigger than for traditional linear media, and that's really a problem in the long run. And as those media become even more interactive, then the design of the pre-design, and if all the assets have to be human-made, then it just doesn't, it's not sustainable, it doesn't scale up properly. And then you get the design of the interaction experience being limited by the fact that there's no generative system to help creators to create better, faster content, right? And again, software right now are mostly inert. So we work at CIAT a lot on human-computer interaction. We do a little bit of that in my lab, but mostly we look at generative systems in the sense that we want intelligent human-computer interaction. We want not just us telling the computer what to do all the time. We also want the computer to eventually be a little bit more proactive so that we'll be more efficient in this interaction, and the computer will be able to do more for us, really. And therefore, we will be able to do more with it. Okay, so if we are looking at modeling artificial creativity, then it's good to look at models of creativity in psychology and in philosophy in general. One simple definition, there's a lot of them, and like intelligence is a concept that doesn't have a well shared, well agreed upon definition. One simple definition is the one by English philosopher Margaret Boden, who said that creativity is the ability to come up with ideas or artifacts that are original, so there's novelty being involved, and valuable. Valuable because they're useful, so there's a notion of utility, or because they're appreciated, preferred, valued by a given community. In art, typically, for example, the art market would make art valuable or not, or individual appreciation would make art valuable or not. There's also two types of creativity that Margaret Boden distinguish. There's peak creativity, psychological creativity, which means the new artifact is novel and valuable for the individual. It's everyday, sometimes called mundane or everyday creativity. That's the idea that for the first time, a little kid draw a house. It's a great drawing of a house. It's really nice. But is it really a contribution to the world? In some sense, yes. In some sense, no. Let's take another example. For the first time, a 12-year-old do on his own a demonstration of the Pythagorean theorem. If he comes with it on his own, it's really creative of him. At the same time, it's not really creative for all the mathematicians in the world because we knew that demonstrations before. Right, so that's peak creativity. Edge creativity, on the other hand, is historical creativity. And in that case, the artifact is valuable and novel for the group being humanity in that case. And so it's like eminent creativity, and here you go towards some of the canonic view around creativity and the notion of genius and etc. Okay, so those are the different types. And then Margaret Boden goes on to define 3 different types of creativity that I will summarize as such. The first one is exploratory creativity. You get a set of elements, and that's important because we use that a lot later on. You have a set of elements, let's say, of the songs from Bob Marley, and you want to create new songs that sounds like Bob Marley. Or you have all the sonat in a particular style of music, and you want to create new elements in that space. So that's exploratory creativity. There's a space that you want to explore. So let's say the space of all the possible oil paintings, or the space of all the possible guitar riffs. And you want to find new areas in that space, areas that have not been explored, where there's novel and valuable artifacts to be discovered or to be generated, which is what we're all about in the lab. Then you get combinatorial creativity, which is about putting together different creative space. Let's say you have the idea, it's quite a creative idea, I think I'm not the first one having it though, of having a cell phone that would also be a video projector. Right? And then you get the space of the video projector, space of the cell phone, and then you get an intersection that can be a creative idea in that case. Or you have something like all the rhythm of dub music and the harmony of jazz music, and you find a new space, you invent a new style that is in between, that is combining those elements in certain creative ways. So that's combinatorial. And then you get the real, and often edge creativity belongs to this category. The real and well-known artists and well-known designers are always viewed as belonging to the type of people that do transformational creativity. Transformational creativity is the idea that we change the boundaries, the frontier, the topology of the space itself. So let's say when Duchamp came up with Fontaine, this idea of putting a toilet in a museum, that was not considered as art before he did it. He framed it, convinced people, and then all of a sudden the field of art would have expanded a little, and objet trouvé would become a recognized art form that didn't, was not considered as such before. There's we all know many examples of transformational creativity because they're the one that we read about when we read about great historical figures. Okay, now I'll take a little break and play a little bit of music, and I'll get you to guess what's happening. So try to find out what's happening in this little excerpt here. So a small excerpt of a piece of music. Anyone has any idea what that is, given what I said, obviously? Exactly. So here it's the Yelton String Quartet with Daniel Tone at the percussion, but the score is composed by a machine. And so I'm going to talk a lot more about that. The composition is called Dead Slow Look Left. We had to give the name. The machine did find the name. Some machines do find names for the pieces that generate. Ours doesn't. And it's a machine that has been learning from human-made compositions, actually made by Pat Metheny, all the compositions of Pat Metheny of the late 80s, and then generating chord progression. And I'll present that system a little bit later in more details. Okay, so I'm going to start going into the work we actually do in the lab, starting with, because that's the area that is the most developed in our lab, by musical meta-creation. So musical meta-creation is really this idea of doing generative systems for music. And the type of canonical problem, which are creative tasks, so they're not rational problems that we can solve in an optimal fashion, that we're looking at is composition. So composition is starting from nothing or from a bunch of existing composition and generate a new score or a new musical notation. Interpretation is this idea of having a composition that is made by a composer and then playing it so as to have an audio signal out. That's the idea of rendering a composition. Improvisation is when you do both at once, if you wish. You're on stage and there's no composition, you're composing and interpreting at the same time. Accompaniment is a more specialized problem that is about playing along with a composition or an interpretation or improvisation. And continuation is a very specific problem that is really coming from the computational creativity community that is about you play something, you stop, and the machine continues in a seamless way. That's a tough problem to solve, but some machines are doing that very well. A funny note here for those of you who are musically inclined, it so happened that, and it's going to appear clearly when I'm going to tell later, that the composition problem, we have machines that we say are human competitive, as in arguably when we make empirical experiment, human can tell the difference between the machine-made composition and the human-made composition. So in other words, we have very good algorithm for doing that. Interpretation, on the other hand, there's competition every year of machine playing classical music or jazz music, and typically within seconds or at least minutes, any any person that is well-trained would tell that this is actually a really bad musician, right? So it's interesting, and I believe it has to do with the fact that composition comes a lot, it's a very cognitive activity in some ways of generating forms, and our brain is not that good, while interpretation often has to do with the body. And 80% of that brain is grown to operate our body, and our body is just magic. It's 70% water. I don't do robotics, but we all know if you search like robot fail online, like just pouring a beer, having a robot pouring a beer is just a $50 million project right now, and it's not sure that it's going to be successfully achieved, right? It's just really, really difficult to replace the human body. So that's just a side note here. So there's various types of meta-creation systems. So I'm going to present systems that solve some of these problems, but I'm going to say a couple more generalities about meta-creation. So there's a continuum between purely reactive systems, the software we use usually. When you open Word, when you open Photoshop, if you don't click somewhere, nothing will happen. They're not autonomous at all. They're not proactive. They won't do anything if you don't drive the process. And then on the other end of the spectrum, you have purely generative systems. You learn from Pat Metheny's composition, you press generate, and it generates a new one. You listen to it, you like it, you don't like it. If you don't like it, you generate another one, etc., etc. But in fact, within that continuum, in the middle, and that's what we, in the long run, more interested in, is that those systems will be interactive. And it will be not just a generative composition system, for example, but more a computer-assisted composition system. So we're looking toward computer-assisted creativity here. So there's the idea of creativity support tool, computer-assisted creativity is really what we're looking at in the long run here. Other characteristics is that some systems are online. Some musical agents are playing live on stage with musicians, and we organize shows where that is happening. Some of the systems are offline. So for example, the composition we just listened to, the computer takes some time to generate it. It doesn't generate it in real time. Some systems are learning from existing material, and if you think about it, human musicians, composers, did listen to a lot of music before they actually become composers. Besides the training they sometimes have, they don't come with no prior exposure to music. So those are corpus-based systems, where the system has been exposed a lot to material before, but there's also systems that are non-corpus-based. Let's say you have a great theory of composition, and it's a set of rules, and you just decide that it's so perfect and formal that you can put it in the computer, and the computer will implement your theory of composition. There's also systems doing that. And in general, there's also in generative systems a continuum between artistic systems. Brian Eno developing a system that generates ambient music. It's his system. If it will generate always different things, but I can recognize it. I'm like, oh, that's Brian Eno, a system composing something here, right? Versus very generic, scientifically oriented system that I will present in a second. And the more it's artistic, the more it's heuristics put in the program that embed the aesthetic of the author within the program versus systems that learn a particular aesthetic that exists or doesn't exist and then generate from there. So in that later case of more generic systems, a good example, and that's why we focus on a lot in the lab, is the idea of style imitation, where you have a corpus, a number of pieces, let's say all the paintings of Rembrandt, that are representative of a style S, let's say the style of a certain period of the career of Rembrandt, and you want to generate new instances that would be classified as belonging to that style by an unbiased observer. So let's say you have all the pieces of music from the band Metallica, and you want to generate a new one that Metallica fan that don't know by heart all the piece would be like, hey, that's a piece from Metallica, I recognize it, right? So we have systems that do that, and that's really the problem that those systems are trying to solve. We're trying to solve that problem. And so often, that's what we do in the lab. We produce corpus-based style machines, and we do style imitation, which is really trying to generate new instances that would be classified as belonging to that style. But we also start doing style interpolation. We start mixing styles, style combination, style transformation. So that's more toward combinatory creativity as opposed to exploratory creativity for style imitation. And then eventually style extrapolation. It's like, give me something that is even more Bob Marley than Bob Marley, if that's possible. So it's the idea of style extrapolation, of pushing the system into new directions, and which of those new directions are actually interesting, relevant, novel, and valuable, as opposed to what directions are just destructing the inner structure of the style and going nowhere. Right. So the system that composed the little piece I just played is, we published it in 2010 with my colleague Arne Engelfeld, and it's generating original harmonic progressions. It's learning from a corpus, so again, in that case, there was a number of compositions from Pat Metheny, and it's just taking as an input a sequence of chords. So it doesn't do melody, it just does chord progression, which we could hear the quartet was just playing a sequence of chords there. And there's an interface that allows the user, so it's computer-assisted composition in a certain sense. You load a corpus, you decide what you give the system to learn from, and then eventually you have a number of parameters that you can drive, and then the system will generate what you asked, and it can do so ad infinitum. Yeah, so that's a screenshot of the interface. It's relatively easy to use. It's quite versatile. It's free. It's online. It's open source. So if you look at our website, metacreation.net, you might find it. Here is a quick example of what the system generates. System generates composition. So if you get the computer to play the composition, it's not as good as if you get an orchestra to play the composition. Here is a little example of a chord progression, because that's what the system does, with like a little rhythm that is not made by the system under it. And it's a chord progression when the system has been learning from some of Miles Davis' composition. So it's more jazzy in a way, a sort of harmonic succession. The system has been used to generate music and chords and electronica, and been adapted by a company in Sweden, Continent Engineering, for an app. And I'm gonna run out of time, so I'm gonna skip that. But it's an absolute blank application. And that was a few years ago, so it has been applied in a way. But at the academic, in terms of academic research, one could ask the question: how good is the system? How good is the system, and how do you, in general, evaluate generative systems of that kind? Generative systems that generate that solve creative tasks. Well, that's not an easy question, because by definition, creative tasks are defined as being the one for which there's no optimal solution. And the typical way you see if a solution is optimal or not is by comparing it to the optimal solution, right? So if you calculate the diagonal of a square room, the optimal solution is given by the Pythagorean theorem, then you can have a traditional way of doing it and stuff, but the way we're going to measure how good your solution is by comparing it to the optimal solution. In our case, we don't have a notion of optimality. On top of that, people might differ in their evaluation, and actually they do. We do not all like the same music, so there's subjective, cultural impression and judgment involved. And on top of that, that's an experiment we're trying to replicate. We've been doing that for the last 2 years. It's quite complicated. There's previous work by Moffat and Kelly here that have been showing that people tend to have a bias against computational creativity. As in, if you tell them it's made by a computer, they don't like it, even if it's actually made by a human. If you lie to them, if you don't tell them it's made by a computer, then they don't have a problem with it. So there's something a little bit freaky about the idea that computer will be creative. And there's good reason for that. The philosophical discussion about who is the author, are humans that vastly superior to everything, and also some misunderstanding, because those machines are made by humans. They're fantastic human creations, and they're in themselves a new type of art, or at least certainly human-made work. Right, so it's difficult to evaluate the system. There's also practical reason. In the one system I just showed you, you can feed the system so many corpuses that the choice and the selection and the curation of those corpuses is really, really important and will determine how successful the system will be. There's various parameters to be changed, and then the system needs to be evaluated on sample output. And like any composer, in fact, that system sometimes is genius and really good, and sometimes is really, really bad. So you have to select what selection of output you evaluate the system on, given that the system can generate not an infinite, but an extremely vast number of possible outputs. One that we won't have enough time in the rest of our life to listen to all those outputs. And then the way the system is used has to be taken into account. And on top of that, in the case of music, composition and interpretation are not independent at all. I can give to the Yale quartet, those guys are good. A bad composition is going to sound great. And I can give a great composition to a really bad string quartet, and it's going to not sound good, right? So interpretation and composition. So here the system is doing only composition. I would decompose the composition from the interpretation. Right, so we did a number of studies, and in fact in the lab, I think we've been doing 8 of them already. And the idea really is to explore a range of qualitative and quantitative, but mostly quantitative so far, methods to evaluate those systems. So really there's a research goal in exploring and crafting new research instruments, new methodologies to evaluate those systems. And the methods often include indirectness. So we won't typically ask people, is the system creative? But we will look at comparative studies and ask people, is the system production comparable to human production? Or can the audience identify which output are system generated? Or we will use deception, knowing that there's a bias against computational creativity. Sometimes we're yet to confirm that bias in every domain. So how engaging is the piece, how boring, enjoyable, simple, complex, organic, mechanical, etc. So there's a various number of methodologies. I won't be able to present all of them at all today, obviously, but I want to take a quick example to give you a feel for it. So for example, here, it's a bit of a Turing test-like sort of methodology, one of the many ones we came up with. And in that case, we play 20 excerpts to each participant of the study, and we ask people to decide if for them it feels like it's definitely human-made, probably human-made, probably computer-made, definitely computer-made. So in that case, we get both a guess and also a confidence level whether they're sure or they're quite unsure. You notice that there's no I don't know options. In perceptual psychology, there's a well-known result about the fact that if you give an I don't know option to people, they will tend to choose that option more often, even though they actually know. And they do have a guess, but they would be shy about it. So here is what the corpus is. It's 28 bars excerpts, and we'll come back to the 8 bars part is really important. In fact, that system that I showed you does chord progression, but it does chord progression that really works for a short amount of time. It doesn't really do beginning, middle, and end. It doesn't have the idea of the hierarchical aspect of music. I'll get back to that in a second. So here we got the various corpuses, and the one in bold here are the one excerpt that was chosen from those pieces are human-made, and that's what the machine has been learning from. And then for each of those corpus, we take a number of pieces from the corpus, so in that case, pieces from Chopin, as well as a number of chord progressions generated by the system, right? And we do that for all these corpuses. And I play you an example, and then we ask people to give us their guess. So here's, for example, we're going to play the game right now. Here is a first chord progression. It's interpreted in a very neutral fashion by a computer playing the piano. So the musician playing it is quite bad, but we are trying to evaluate the composition on time here. We think the first one is human-made. We think the second one is human-made. Right? So it's about half-half, which is what we find in general. In fact, the first one is an harmonic progression from Chopin, from the corpus of Chopin, and the second one is computer-generated based on the corpus from Chopin. But as you see, the task is not that easy. Music is a bit of an abstract art as well, but the system seems to work well. And in fact, we do find with 87 participants in that case that whether you're a trained musician that has learned composition in a conservatory or in a music school, or you're just a layman and a non-musician, people actually are not capable to identify computer-composed pieces above chance level in a way that validates our system. Interestingly, expertise doesn't make any difference. It makes a big difference in the qualitative comments. The experts have all sorts of reasons why they're pretty sure this is the computer, but they're as often wrong as the non-expert. But the experts have a lot of rationale around it. That's what's interesting. I guess that's what expertise is. And then that allows us to conclude that the system is human competitive. at least for those corpuses, right? Maybe you wouldn't be able to do it if it was like for pop music or for jazz, I don't know. But only, and that's really the limitation here, only because these are short excerpts. And if we would do the same experiment, and we know that with longer excerpt, like more than 16 or 32 bars, then it would be clear that the system is getting the style, but is meandering. You know, it doesn't have a sense of hierarchy in the music. So sequences of notes usually are phrases, sequences of phrases from parts, sequences of parts from pieces, and there's really a whole hierarchical structure to music, whether it's classical music or pop music or electronic music. And this particular system doesn't do that. So we wanted to expand our research in that direction, and we did a number of systems, sometimes met with failure. There was a great system that's really inspired by cognitive science and the way the brain processes information, inspired by the hierarchical temporal memory framework of Hawkins, which is really well known in cognitive modeling. And then the formalization of it, but it didn't work. I mean, it probably did work like a 12-year-old would compose, but for us it was not necessarily that satisfying. And so we keep on working. There was the PhD of James Maxwell here, and we developed our own model of learning and generating music, still using symbolic notation. And in that case, same idea. We feed the system some music, but the system will build a hierarchical representation of the music. The model is quite complex here, and therefore the system has a sense of musical development. So not only at the phrase level, but also how to sequence various phrases, and eventually even how to sequence parts. So I won't have time to get into any detail, but it so happened that this system has been applied in a software called ManuScore, which is great, allows composers to, for example, select their own composition, and start composing a new composition and be like, oh, given what I did in the past, how would you continue that melody? So all sorts of tasks in music, like harmonization, for example, can be very daunting. It can be, you've done it for 10 years, in a studio it's always the same. If the machine could learn how you do it, then you would have a few corrections to make and it would save you days. Right? That's really the idea of computer-assisted creativity here. And sometimes you want to be like, oh, but what if I would add to the corpus a little bit of that other composer's material? Maybe it will bend my style into a certain different way, right? That's really where we're going here. We did a formal evaluation of that system with 42 participants, and again, they could not segregate between, in that case, not between the generation, between the computer-assisted composition and between the non-computer-assisted composition where the composer was using a normal music notation software. Okay, here is an example of the results that I want to play because we can hear an articulation between two parts in that example. So it's computer-assisted composition in that case. It's not only machine-generated, it's been edited by the composer. So here you can see the transition between two parts, like a part that is a little bit more rhythmic and then a part that starts more melodic. All right, and then we did all sorts of other studies because we were all excited about those early results, and so I'm not going to go through like, I don't know, 50 publications we made on those type of things, but at some stage we were like, okay, those systems are composers, there's various types of algorithm, can we compare and identify the qualities of various algorithm? So we start comparing our model with the model of the factor oracle, which is typically developed at IRCAM in Paris, and the variable order Markov model, which is François Pachet's work a lot in Paris as well at the Sony CSP lab. There's a couple of laboratory and quite a community around this type of work. And then we wanted to try to quantify how those systems would create and compare them. So we did studies in that direction, and then we developed all sorts of other systems to generate rhythm, systems to do computer-assisted rhythm making, where you start playing the drum, and then the machine learn how you play the drum, and when you stop playing one part of the drum, you can play some other part of the drum, and the system continue in your style. Therefore, you can build up rhythm that you actually can't play, because you have only two hands, or because you're not that good of a drummer. We did system to organize and retrieve sound in real time, all sorts of other application, all those ideas and algorithm. But what I want to go to is the move from symbolic signal and symbolic computation, and AI is really geared toward automatic manipulation of symbolic information, toward solving, so that's composition, towards solving the interpretation problem, which is how do you actually make sound out of it. And that's really the new, another set of research that we've been conducting, and we've been working with Arnie and also with Barry Truax here at SFU on automatic soundscape composition. Barry helped a little bit in the evaluation and was very useful in his input. And so here the challenge is to generate system for soundscape composition. And soundscape composition is this idea of doing soundscape recordings and putting them together in a way that the listener can recognize the source material, so it's, the recognizability is maintained, the knowledge of the environment and psychological context is invoked, and the composer's knowledge of the environment and psychological context influence the shape of the composition at every level. So it's basically the idea of composing with concrete recordings. So it's sort of a version of concrete music. And so we did a system that generates that, and to do that, it's not just composition, you need to generate audio, right? So you have recordings, because the computers are not going to go in the wild do sound recording, and then you need to generate things. So we did a system, and we showed that it's a lot harder of a problem. And the experiment was showing that it's better than a random system that puts those recordings randomly, but it's not quite as good as a composer, which give a glimpse of hope for composers here. Now, I'm joking, we really never want to replace composers anyway. And so there's quite a bit of work building up on that. We now have a new system that is interesting and more computer-assisted composition in the sense that you give him a sentence, a language query, and he's going to parse that sentence, find synonyms of those words, etc., look at big audio database, such as the freesound.org database, retrieve a bunch of sound that are representative of the element, semantic element that are involved in that sentence and the relationship between them. Then we segment all those files into background and foreground type of segments. So sometimes in a recording of a forest, you have the background sound of the forest, and then all of a sudden a bird is singing. That will be foreground. So those are perceptual categories. The classifier and the segmentation system here is extremely fast, and it's been shown to be better than most human at the way it does it. And then after that, we have a sound composition engine, and that's really the weakest link right now in that particular system that put together those sounds to do a soundscape composition. And so, example, if you enter to this system, the sentence or the expression, the waterfall in Thailand, the system will always return something different, but here is an example of what it can return. So it's a lot of sound that are sort of relevant to the actual input here. So imagine in sound design for film, video, or even for video game for that matter, at least the system will retrieve from that big database all sorts of sound that are sort of relevant for you to use. We'll segment them into the background part, the foreground part. You get a lot of work done. Instead of trying to remember the name of those files on your hard drive, which when you have over 1 million sound in a data bank is not quite easy. There's other engine to search sound though. A city in the bush. If you enter that, then you get this sort of output, I guess. It's funny because it's the bush and city sound. And then you can push the system into more abstract directions as well, because when you start looking at those type of words, in a sound data bank, then it's a little bit more abstract. We're still working on that on this particular system to be able to control the generation in terms of affect. When we want to control the eventfulness of the composition, the soundscape that is generated, and we want to control how positive or negative the valence of the composition, and we know how to do that. So that's going to be sort of one of the future paper here. So that's soundscape composition. Another audio-oriented project, given that the composition engines were working well, is this idea to say, okay, if the body is that important in playing music, let's try to find a type of music in which the body is not that important. And then it was electronic music. We're also big fans of electronic music, so that was sort of an easy choice. And we have this system called GURP. It's a project, actually. There's many systems coming out of it. The Generative Electronica Research Project with Chris Anderson, Annie Engelfield, Tristan Bayfield, and myself, mostly. And the idea is to really learn from existing electronic music pieces and then compose new ones. And we focused on house music and breakbeat for a start. And we developed our own algorithm. There's quite a bit of work in analyzing the piece, a lot of human expertise in that system at first, but it gives then pieces that sound like that. I have hours of it. Actually, I do. There's an album on the Chord Punch label in the UK that is generated by one of these systems. So if you guys, I think it's free actually. And Chord Punch is releasing only generated music, so that was an easy fix. And the validation is ongoing, but the validation here is much more pragmatic in the sense that we organize algo raves, we organize parties, we got the system to play in clubs, we release albums, we look at concert sales and things like that, more so than empirical experiment, because we have confidence that some of that stuff is good. There's no doubt about it at some stage, at least as sort of composers and developers of the system. If we like the output, we like that's what I like. In fact, this system is available commercially or has been commercialized by Metacreative Technology, which is a company that is supported by SFU Venture Lab. Yeah, that's the name. And it's right now available as a plugin for Ableton Live, which is the most used audio production environment with over 6 million users. Then we looked a little bit more in depth at the audio part and looking at sound synthesis. So we worked with the same Swedish company that are building this very, very nice, very well designed, I mean, Swedish are so good at design, synthesizer called the OP1, and they sold a lot of it. And the question was like, this type of synthesizers and modern synthesizers in general, the search space is massive. In fact, the number of presets, the number of sounds you can make with a synthesizer is just an order of magnitude less than the number of atoms in the universe. Like it's 10 power 78 or something like that. It's a lot of possibilities. And so if you search for a particular sound, let's say the sound of the tap water in your bathroom, very random example here, then you're going to search for long, even if you're a specialist of sound synthesis, like to get really close to that. So we decided that we would try to automatize the generation of presets and of sound making for that particular synthesizer. So the challenge here is to finding a set of parameters that gets you a preset that is as close as possible to the target sound. So you have a recording of the sound of the voice of someone, and you want to get as close as that. A recording of the bass in Billie Jean, and you want to get a sound as close as that. And after that, as a musician, you can play around that preset and change it and modify it. So here we use evolutionary computation for this type of approaches. And if you guys have any questions on any of the technical details, I'm happy to give short 2 or 3 minutes explanation of this quite powerful algorithm after the fact. It's not that complicated to understand. Evolutionary computation is really coming from what we know of natural evolution. the evaluation here is showing that the system is quite successful, and we know that because if we give a sound that the OP1 can actually make, then it retrieves the preset for that sound. And sometimes it gives you also other way to set the synthesizer to give the exact same sound, which the designer of the synthesizer themselves didn't know was there, right? So they themselves learned things about it. We're working with teenage engineering to deploy it. It's been a while. It's complicated because the system takes a lot of things. But let's listen to example just real quick here. So that's a target sound, the sound I want to make. I'm going to replay that with the volume on. So it's a recording with a microphone of a note of a piano, right? And this is now a recording of the synthesizer. So our system give how do you need to set the synthesizer to get that sound, and then that's how it sounds. And that's pretty close, even though this is not a piano, this is a synthesizer. And so sometime we looked for sound that the designer themselves had no idea if the synthesizer could do it or not. See, I put those things so close to each other that it's really complicated to play them. Let me try again. It must be here is a more percussive sound. And you can see here, you can hear a little bit of a difference in the treble, flute. And the flute of the synthesizer sounds very synthetic in that particular case. So when the synthesizer can actually do those sounds, it converges well. When it can't, then it's harder indeed. And now we extend that work by going for, instead of generating a preset for synthesizer, let's generate a synthesizer. So we give a bunch of sound, and I want a program that can generate all of those sounds. That's what we call a synthesizer, general synthesis problem. Project started 8 years ago, 7 years. 7 years ago, with like a series of students failing at it. And Kivansh, who did kindly the introduction today, is the one who is in charge right now. I wish him good luck. No, we have encouraging results, jokes apart. So I think you might graduate sometime. Okay, very quickly, I'm going to take another 10 minutes just to wrap it up. It works for music. Does it work for other areas? Visual art, game design, video, it sure does. A parenthesis project was the Dreaming Machine, where we looked at generating interesting visual art by looking at theories of dreaming. First, Ben Bogart did a master here on representing the memory of with using self-organized map. And then more recently, I got him doing his PhD to try to look at neurobiology of dreams and implement, to the best of our knowledge, collective knowledge, how dreaming works. And then we got the machine to look at movies and to look at the TV. The machine doesn't mind, or to look at the world, actually. And then the machine starts dreaming about it. So looking at it during the day, dreaming about it during the night, it does sometimes look good. More practical type of systems that allow to do non-photorealistic rendering. You give a number of pictures, you choose a style, it does a rendering in that style, and that way we do impressionism, montage, cubism, futurism, abstract expressionism. It also allows to do video morphing and all sorts of things, and we're working now with a local company called Generate, which has a nice application that you might want to check online. It's a iPhone, it's a mobile phone application to implement some of those part of the system into the application. And then we, with my colleague Steve DiPaola, we developed a non-photorealistic rendering system called Painterly. I wanted to use his system to try to see if we can do style imitation in the context of non-photorealistic rendering. Non-photorealistic rendering means it's basically that imitation of painting or drawing or anything that is rendering graphically but not using the direct picture. So if, for example, you get a rendering of, so that's a Rembrandt, and on the right here you have an example of actual painting from Horton, and then here you got a rendering of Steve in the style of Rembrandt, and a rendering of Steve in the style of Horton. So what the system does here is really learn from pairs, like pictures and rendering of those pictures by a painter, and you try to learn what the transformation is, like what is in, and try to abstract the style of that painter, and then we can apply that on any pictures. Indeed, that's me in the style of Rembrandt, and questionably like probably, I mean, clearly in that case not as good as Rembrandt, me in the style of Orton, for example. Yeah. So that's style imitation in the context of visual art. Here we do it for video game as well. We did the best paper award, but we ended up sub in the competition of generating Mario level with a system that generate levels for video game. And here you can see that we're getting closer to actual application that are certainly very useful. And then more recently, with a new SHUG grant and Arnie, Jim Bizoki, and a number of great students, we're working on audio-video meta creation. How do you generate sound for a particular video? And eventually, the idea of generating both video and sound. We also have a system that we're working on right now with Jianyu and actually William, that is here in the room, that generate music video for music. Since we have a system that generates generative music, electronic music, we might as well generate music video for it. And then the scaling problem. So if it does work in a variety of areas, how much is too much, right? And one domain that is really hard because there's a strong uncanny valley is body movement and human movement. Our brain, through our eyes, is so well trained on recognizing humans and as well their movement signature and the way they work. Can we artificially generate movement that is believable, and can we control the generation? So we did a number of systems that have to do with generating movement. We got a best paper award early on with that, but the newest generation of systems that we work on is really applying this idea of style imitation to the generation of movement, and the idea is to learn from mocap data, where we have, in that case it was 2 actors that do a series of movement, walking, sitting, pointing, things like that, and for each movement they would do it 9 times. They would do it in the most natural possible way. They would do it as they feel super happy, or they act as it's super happy. As they're happy and excited. Are they just excited, not happy, not sad? Are they just excited and with a low valence? So that's typically angry, distressed. As they feel not excited, not sleepy, but they feel sad and miserable. As they feel, etc., etc. So all the corners of this valence and arousal model we tried to cover in that particular take. And then the machine learns from it, and then we can ask the machine to generate either combination here that have not been seen, or even transition between those combinations that the mocap has never seen. So in other words, we'll be able to generate movement for once, which is not that easy, and then to control that generation in real time eventually, but we're not there, to control that generation in terms of valence and arousal. So we can generate new movement that has not been seen with expressivity that has not been seen either. So I'm not going to play with this, but I think I have a nice, yeah, here is an example of input. So that's actual mocap data here. Oh, of course the video doesn't play. Oh, I know why. It's because I moved everything. Oh, that's bad preparation here. And then I wanted to play a transition. Let me. Well, during the question and answers, maybe I'll get back to that. But and then we started looking at style extrapolation. Like, can we actually get a generation that, if this actor was playing happy, that actually we try to be even more happy than he was capable of playing? And where exactly does that break? Because at some stage it's not going to look human anymore. Like humans, it's going to emphasize the traits of happiness in movement in a way that will stop being believable. So we're looking at those generative tasks with the long-term goal to really create what we call motion graph, parameterized motion graph, that will allow really to have real-time control over the movement, the generation movement of virtual characters. So that's really, and that's really the scaling problem, because movement is a lot more information than music, for example, just in terms of amount of information, and as well in terms of perception. We are a lot better and a lot subtle, and our perception of movement is a lot richer than our perception of music, arguably. In other words, validating the system and making the system work is a lot harder. both at the computational level and also in terms of the empirical studies of getting the believability out of it. So I'm going to conclude now because it's been already an hour. So just to conclude, and that's maybe the takeaway thing, is what is computational creativity? Well, it's the idea of automatizing creative tasks, and creative tasks being defined as being opposed to strict rational problem solving, so tasks for which there's no clear, optimal, better solution, or best solution. And the key research question we're looking at is, what is creativity? Can we model it? So trying to develop computational model of human creativity. And here when I mean computational, the in fact mathematical model. It so happens that modern mathematics is complex enough that you often need a computer to just formulate and run the model. Artificially creative systems, so meta creation. How do we evaluate those systems? If we have models that do work, and can we make the system being as good as humans? But can we make sometimes the systems being even better than humans? So for example, there's a well-known system, it's not ours, so I'm happy to talk about it, by Dan Ventura, that is learning how to generate sad music by learning from sad musics found in films made by over 100 composers. And then humans find that the music generated by the system is sadder than any of those composers' work. And in a way, it's a little bit like you would have those 100 composers in the room, and for each sequence of notes, you'll get them to vote on what is the best note to put next. And altogether, the collective intelligence, which is what the machine really learns, is a little bit better than their individual skills, which is an interesting idea for those who are interested in individual versus collective intelligence. And then eventually, when those systems are really working, we're looking at computer applications in computer-assisted creativity and a system that are here to support human creativity. I personally think that we spend too much time interacting with computers, and HCI is important. We need better interfaces to interact with computers, but most importantly, we need computers to work more, and we need ourselves to spend less time in front of them. I think we can all agree on that. More generally, if I want to open up in a sort of a debate here, the ability to develop a new tool has been a defining characteristic of human beings from the invention of the wheel to the development of personal digital assistants. Technology has always been shaping us, and in recent years, the computerization of society, pretty much every domain of it, has opened the doors to the automation of information processes. So that's really the idea of artificial intelligence and computer science in general. And so the vision here is that we should get machines that are more autonomous and get them work for us. And because there is no pre-science, the way we do that, we started by automating, basically there was AI started with military applications, mostly. And now it's important that it trickles down to creative applications and to the creative tasks that are defined earlier on. And so in a way, for me at least, and at CIAT, the School of Interactive Arts and Technology, where we mix art, design, and science, it's really a vision to try to engage creative people in the shaping of new technology, give meaning and cultural relevance to technology, and push for computational literacy to get the creative industries and the creative people and workers engaged with the design and the development of the technology. So we're not looking at them being just user of those computer-assisted systems, but also being involved in the design of them. And by doing that, they raise a great awareness around the systems and the philosophical questions that are associated with them, and therefore will become better citizens when it comes to the political debate, which is vastly absent around what do we do with technology, why, and how. Right, so that's it for me. Just a couple of announcements. This year in Vancouver, for the students in the room, we organize a motion, movement, and computation workshop. It's the second one. We just got a grant this morning for it. From Shirk, ACM Library Proceedings. We're going to have a great dance company as part of it as well. And then this year, I so happen to be a chair of MOCO, but also a director of ISEA 2015. And as part of ISEA, there'll be a number of the systems like the one I presented today that will be showcased. There'll be an algo rave, where there'll be generative dance music and live coding. There'll be musical concerts where artificial agents, musical agents, and musicians will play together. And there'll be all sorts of events, a great opening at the Vancouver Art Gallery, and a great program of talks, over 300 of them, over 180 artworks, plenty of workshops, plenty of tutorials. And I think the call for volunteer is going to come out in the next few weeks. So try to look up for it, because it's a great way to get in for free by giving a little bit of your time work. It's going to bring around 600 to 700 people from out of town, from all over the world. And we're really excited. We have a great list of speakers here. So that's it for me. It's been just a little over an hour, so I'm open to questions if you have any.
Thank you, Philippe. So, question? I should just remind you to repeat the question if you can.
I will.
Another question?
Yeah.
I'm curious to know, from your perspective as an artist, just personally, what you find the most engaging or inspiring about working with a machine that can provide you with assistance in creating.
Yeah.
So is that part of what drives you to work with students to create these tools?
Yeah.
Or is it something more beyond that?
Yeah, but that's a great question. So the work I presented today is really the work of the lab. It's mostly academic, and I think I did put forward the research questions and the type of answers we were looking at. Personally, as an artist, I've been so busy that my practice has been, I've not been as active in the last few years, but still, I typically don't use any of the system we do in the lab. And you know, those things are totally not mutually exclusive. I mean, even when we commercialize some of those systems for artists to use, it doesn't mean that you can't do it any other way, right? So it's not technology is rarely about replacing what was before. So the same way that electronic music didn't replace classic music, it's just, you know, you add to it. And so these are adding possibilities for artists in what some of the tools are presented, obviously for composers, you know, some of the tools obviously for people doing animation, etc. But nobody is going to ever be forced to do it. It's just so happen that if those tools, and we hope they are successful, they might just be adopted because they allow for better work to be done. And so while the information technologies are doing to information what the Industrial Revolution did to mechanical work, there is a pushback and there's debate to have around that. So when the mechanization of sewing was happening in England in the 19th century, the biggest riot in London was there. People were really against it. A few years later, everyone agreed that was allowing for better sewing. Not necessarily for better, we still have petite main in Paris doing haute couture, no problem. But it just allowed to produce faster and more efficiently, really high quality things. And sometimes, a little bit like we look at creativity as it is and creativity as it could be, it allowed for doing some type of sewing that you can't do manually, right? And so with those type of machines that are automating the manipulation of information, that's really the AI project in general, it's happening, obviously. And since, you know, they fly plane for us, and we need to have debates around it, and there's a pushback. And so here, it's a new field that is about automatizing creative tasks. So there's obviously pushbacks. When I give talks in art schools, there's a lot of people that hate me. You know, they really, really don't like me. They're scared of me. And in fact, they're scared of the machine, right? Usually, fear comes from ignorance. In their case, it does. Yeah. Yeah.
I think it's really interesting. It's really creative. If only we knew anything related to successful
I think that's a fallacy. You know, I might be wrong in that, because there's studies showing that for the first time in history, machines are starting to replace humans' job. But in general, when the lawnmower was invented, the gardeners were like, "Oh my God, we're going to be jobless in no time." Well, guess what? They're still gardeners. And a few years later, all the gardeners were like, "Duh, it just allows for better gardening, and I can concentrate on other things and do other things and do more and do better," right? So this idea that machines which are never autonomous. I mean, if you don't like a machine, you turn it off. And by the way, the lawnmower is a lot more dangerous than any of those machines. When there's a problem, this anthropomorphic instrumentalism is what I believe in. We develop the machines we need. It's not the machines that are going to compete with us, in no way.
But my question is, I was wondering, like, you guys dealing with lots of like art pieces and original music or video that like people put lots of like effort to make it. So how do you guys deal with all this copyright issue or intellectual property or ethics?
Yeah, so that's a philosophical debate. I know people in law that are making, PhDs or are professors specialized in that area. It's really the problem of authorship, right? Who is the author? When the composition, for example, the first example I played, system learns from Pat Metheny, generate new Pat Metheny, people can't tell the difference in the style of Pat Metheny, so style imitation. Who is the author? Pat Metheny, the programmer of the systems, me and Arnie, the algorithm itself, and the machine, that's really a philosophical debate. A priori, all of these have something to do with it, with the output, but that makes the thing complicated. And we are here, certainly in terms of law and copyright, in a gray area where, and that's not the only case, where the law is a little bit behind in thinking these things through. But, you just talk about copyright of music and free downloading online, and you can tell the law is a little bit behind already. Like, people try to forbid things that, they won't be able to, etc., etc. So that's one of the characteristics, I guess, with new technology, is that they're new, they'll be newer tomorrow, there'll be newer ones tomorrow, and it moves fast. And that's actually a technophobic argument. There is sometimes a sensation, even for people like me, arguably an expert in artificial intelligence, to run behind. That is myself, and we all do that. Every day we discover, like, oh, they have a machine that does that? No, I had no idea. I was not consulted. And then it goes back to, I don't want to enter into a longer philosophical discussion, but Jürgen Habermas, for example, from the Frankfurt School, has been yelling that in the days quite a bit, that there's a need for pre-science. There's a need for a debate of what science do we do and why. And you notice computerization of society happened, and you've never been asked. Your kids are going to spend all their life with machines on them, and you've never been consulted. Right? So that's a problem, but that's a problem that is a little bit beyond me, right? At this stage. Yes?
Thanks for your talk. You're talking a lot about how these machines replicate other composers like machine.
Yeah.
So I was wondering if they can analyze a lot of music and come up with a new genre for some people.
Right, so the question, I forgot to repeat the question. The question is, so we're looking at style imitation of music, having music that imitate the style of what we feed them, right? And the question is, can we, so that's what I define, what Margaret Bowen, to simplify, call exploratory creativity. You get a creative space and you find new, novel and variable elements in it, the space of all the oil painting in the style of Rembrandt, the style of et cetera, et cetera. And then, can we generate new styles? If I understand your question, that's what you're asking. Well, that's the idea of style interpolation or style combination. And again, with some of these systems, we can already do that. We can have, okay, let's take house music for the rhythm, and let's take jazz from Miles Davis for the harmonies, and let's put those corpuses together and try to generate something. To be very honest, I just will start students on that in September. So if you come back in a year, I might have better answers for you in terms of whether or not it works, when does it work, why does it work, when does it not work, because surely there's a lot of cases in which it won't work, and why. Yeah, but it's certainly in the agenda to try to look at style combination, so combinatory creativity, and also transformational creativity. One algorithm that is interesting these days called novelty search, which is the idea that you feed, that's the way I would apply it, but the algorithm is a bit more abstract than that, but this idea that if you feed me with a number of existing styles, can I find a type of music that is the further away possible from all those styles? So that's really the idea of looking at a bigger space and trying to find part of the space that are completely unexplored. So that, for example, is an avenue for looking for some sort of style discovery, right? And again, typically that's transformational creativity, and that's what humans are, for now, really, really good at, and I know no example of machine doing that. So when Duchamp come with Fontaine and say, now this is work, this is artwork, this toilet here now is artwork, and he's making an argument about it, he's framing it as such, he's changing the space, he's making a change to that creative space, and he just, in that case, allow for objet trouvé to become a new style of art making, right? I know of no machine doing that, right? But it's certainly, at least at the academic level, something we might want to look at. I like style imitation because it's really functional, and I like this idea again that in that continuum between software do nothing for us, we have to click on buttons for days, versus software do everything for us. I think it's in the middle that the interesting things will happen. Yeah.
I think computer composed music are fantastic. So basically,
You like computers? No, I'm joking.
yeah, it's unpredictable. So basically, we are learning from different kinds of music types, and to try to create something new. Is that right? So, what's your opinion of self-learning of computer composed music?
So, okay, I'll ask you to, before I repeat the question, I'll ask you to repeat it. You said, what do you mean by self-learning?
Self-learning. So now we're learning from other kinds of music. It's not
That's right.
self-learning.
That's right.
Artificial intelligence, it's self-learning.
Yeah. Okay. Interesting. So self-learning. Okay. I wouldn't call it self-learning, but think about it. So the question is, we do style imitation with computers because all the systems are corpus-based. They look at human-made composition, and that's where the real creativity is. And all they do is imitate, right? The imitation machine. I call them style machine, but they're imitation machine, right? And you show my face in the style of Rembrandt. It's not as good as Rembrandt, but it captures something of the style. Same for the music machines and the rhythm machines and etc. Now you're asking, what if we don't feed them the corpus? Well, what if a human composer is asked to compose that has never heard music? Now it's going to be really weird music, and actually the notion of music would probably not be evident for him. So, I mean, culture is an historical construction, and there is no way you're going to get a machine to play well-tempered clavier style of music or pop music or rock and roll or invent it on its own, right? There's people, though, modeling this cultural evolution and these cultural constructions. It's a bit of a different field, but there's people who are doing that. We do it for language evolution, we do it for developmental capabilities of kids, we do it so those AI systems are also used to make simulations in cognitive science, especially of how did we come up, why, for example, music is appealing to us, and how did it evolve to be that way. There's very precise answers to those questions, and that's more addressed by communities around music perception and cognition. There's a vast array of knowledge. And ourselves, we tap into that knowledge to develop some of those systems. But I don't believe in machine not being fed anything, coming with anything interesting, just the same way that I wouldn't believe in a human having no interaction with other humans, being not having heard anything, being necessarily generating interesting music as such. So that's not where we're going. Now, one of the things we did is what we call in mathematics a fixed point experiment, where if this machine is a composer, we feed him an initial corpus, and then it's going to generate, let's say I feed him 100 songs, folk music from Eastern Europe, we did actually that, and then he generates a new 100 composition in that style. Then I get him to learn from the one he's been composing, and then generate a second generation based on that new corpus that is bigger, right? And then the question is it the case that he's going to stay strict to the style, or is it going to start drifting and eventually modifying, transforming the style? So this idea of style transformation through iteration of those processes. Because again, one of the nice things with machine that they're really, really stupid, but on the other hand, and they're very, very fast. So we can get them to do things that you wouldn't ask human composer to do, because the composer would be like, you're kidding me. And so you can really, again, try to look at those processes, not only to mimic and model and try to understand creativity as it is, but also find new processes that will be creative process, but that creative process that can't be asked to humans, where we need the machine to go through the process, even though the outcome will be a creative outcome. Yeah.
Thank you.
You're welcome. Simon?
My question, perhaps you've already answered some of it in the latter part of what you just said, but is that in the examples as you provide your English, the systems are provided very expert purposes in particular styles or some particular composers or musicians that are known to be excellent for just. So yeah, what happens, or are you aware of the research where there's been, whatever manner, been corpuses that are non-expert or generalized sound,
Yeah.
or inclusive of language and environmental sound as well as
Yeah.
physical stuff. So,
Yeah, yeah. So, I do know, we didn't do research like that, but I do know people who do. So there's François Pasquier, one of the person I mentioned that we compared our model with, has been focusing for a while on systems that are solving the continuation problem, where you play the piano, you stop, and the machine continues in your style. They were doing even radio shows about it, with experts being incapable to tell when it was this fantastic jazz man playing or when it was actually the machine. So those systems are really good. But again, that was expert. But they also did experiment with kids. Kids playing. And this is a question and answer. The kids play no training. They're just the kids like super energetic, as you know, kids, right? And then the machine plays back, and the kids listen, and there's a bit of a difference in the machine, and then comes something, and then try something like contrast, for example, like being like super, like, and listen to the machine, and the machine, and then it's actually, so there's, I won't summarize the paper, but there's a number of journal papers around those studies of reflective interaction, where you sort of interact with an image of yourself, in the sense that the machine is picking up your style and is like, sort of doing this imitation game, but in real time with you, and it's not like looking at yourself in a mirror, but it's an interesting thing, and they observe a number of very, very interesting characteristics, so much so that they, I think they have new funding to exploit that in a pedagogical context and things like that, yeah. Because indeed, all those, I'm not interested so much in pedagogical application, but, obviously, some application of all those systems are eventually pedagogical.
Thank you very much for your presentation. Thanks
You're
for having
welcome.
me. Well, thank you, everybody. This is the last gathering of the colloquium for the semester, so I wish you a good summer term. And that's all for today. And we'll go out with some music.
Yeah, I'll play some music in the background.
Okay.
Machine-generated music, obviously. I want to thank as well my friend Jean Ann from the collective Instant Coffee that joined us, albeit only for the last 5 minutes of the talk. I'm sure he discovered how far Surrey is from downtown.